Hello everybody, my name is Joaquin Ravello and I am the 2020 President of the Canadian Student Space Initiative, or CSSI for short. In light of a few new experiments that we've been doing with nozzle geometry and specific impulse, I have been creating these few videos to help inform the viewers of what we've been up to. We've also made major edits to the website, so you can find that at cssi.space alongside the new report and a previous report we did on regression rates that we actually never ended up posting on the website. So make sure you check that out. You can also find a video vlog of the entire experiment, filming up our setup, our procedure, everything that we did. You can find that in the description below or in the website. To set the scene for these new experiments, I want to talk about specific impulse. Specifically, what it means, why rocket scientists use it, and how it can be calculated. Specific impulse is a measure of the change in thrust per weight flow rate, or dWdt. This represents the performance of a rocket and can simply be thought of as an efficiency measurement, because the engine with the higher specific impulse is more efficient because it produces more thrust per the same mass of propellant. So if you were to run a higher thrust engine with less fuel, you're by definition essentially making a more efficient system. The equation for the specific impulse can be seen right here. I find it rather interesting that if you were to actually write out the SI units of specific impulse, they end up canceling out, a lot of them, and you end up with an expression that is only seconds. So in essence, specific impulse has units of seconds, but it doesn't really mean anything in that respect. As you can see, since the weight is just a measure of the mass times the gravitational constant, this expression can be written in terms of the mass flow rate. The equation with the mass flow rate becomes very useful for any theoretical predictions and calculation, because we can theoretically calculate any specific impulse by setting something known as the design thrust. This is simply a parameter that adjusts the specific impulse based on what you predict your thrust to be, which alongside the mass flow rate allows you to calculate the specific impulse at that thrust. So what is the mass flow rate? Well, it can be written as this equation, which is a monstrosity from the look at it. But if you take a closer look, you'll realize that the equation is just a bunch of isentropic flow variables stuck together. The derivation is rather interesting, as seen in NASA's website, which I'll link in the description below, so make sure to check that out. Doing some derivation of the specific impulse equation, we get these two variations of the equation. As I mentioned before, equation 3 becomes very useful if I want to calculate the theoretical specific impulse for a given mass flow rate and a gravitational constant. However, during the experiment, equation 4 can be used to calculate the experimental specific impulse, as we did in our paper. The impulse is just the area under the force time graph, and the MP term is just the mass of the propellant. As you can see, this equation becomes very handy when doing experimental setups due to the integral, which is simply just the area under the time, the force time graph, which is simply integrated using log-or-pros integrate function. Hence, you can find the specific impulse just by using a force sensor, as we did in our previous experiment, which you can actually see the setup right here. Now, as we saw in equation 4, we need to actually calculate the mass of the propellant. This is actually much more difficult than you might think. Propellant mass can be thought of as the sum of the mass of the fuel and the mass of the oxidizer. The fuel mass would be the mass of the paraffin wax, which is measured by finding the displacement of the mass before the fire by putting the combustion chamber on a mass, and then measuring the combustion chamber again after the test fire and finding the difference between them. However, as I mentioned before, in a hybrid rocket engine, the mass of propellant also includes the oxidizer mass. A quick summary, the role of the oxidizer is to intensify the combustion of the fuel. Since the oxidizer we use in our hybrid rocket engine is gaseous oxygen, it becomes nearly impossible to accurately measure the amount of gas that flowed through the combustion chamber. Hence, we can use the oxidizer to fuel ratio, which is simply the ratio between the oxidizer and the fuel, and can be calculated to find the oxidizer mass. I've even shown the very simple derivation that can be seen right here of how we get to an expression that relates the oxidizer to fuel ratio to the mass flow rate of the rocket. And you see, if we make the substitution for the mass flow rate, we get this monstrosity looking equation again. Therefore, the mass flow rate surprisingly becomes a necessity to calculate both the theoretical specific impulse and the experimental specific impulse. You might be wondering right now why we can't use basic stoichiometry to find the mass of the oxidizer used in the total combustion, as we are just talking about the combustion of paraffin wax, which is a very simple hydrocarbon. However, stoichiometry cannot be used in this problem because stoichiometric ratios would only measure the minimum amount of oxygen needed to completely combust the mass of the paraffin wax. And this minimum amount is not the same amount of oxygen that flows through the combustion chamber. Since the oxidizer is supplied at a constant rate through the combustion chamber, extra oxidizer will undoubtedly be used in the combustion. The excess oxygen allows the reaction to continue combusting at its same high initial rate throughout the entire burn because of the sustained flow of concentrated oxygen. Without excess oxygen, the concentration of oxidizer would decrease throughout the entire burn. While this would still create combustion, it would create an exponentially decreasing thrust throughout a longer burn, which is not ideal as effective propulsion systems are designed to deliver the highest thrust for a sustained period of time. Most rockets, as a result, do not operate stoichiometrically. For example, consider the Delta IV rocket, which runs on very rich hydrogen propellant. As a result, you get a lot of unburned hydrogen exiting the rocket, which generates thrust more effectively because of the lower temperature caused by the excess hydrogen. You also get the cool spectacle of the ship getting incinerated by the excess hydrogen exiting the rocket. As a result, these stoichiometric ratios cannot be used in a reaction like this. So as a result, we must use the OF ratio, which is calculated using the equation here, as mentioned before, to find the mass of the propellant and hence the specific impulse. So in review, specific impulse is measured as the change in thrust per weight flow rate. It can very much be thought of as the fuel efficiency of a rocket, similarly to the kilometers per liter of a car engine. Anyways, that's it for this video on specific impulse. Thank you very much for watching. Please make sure to check out the new report we posted on our website, cssi.space, or in the description down below. Thank you very much for watching, and until next time, see you later. Thanks.